Hey there, it's Modern Retro Tech, and today we are continuing with Advent of Code. Last time we did days 7 and 8, today we are doing days 9 and 10, hopefully. And while I was not streaming, I added one little feature to our REPL interface that we are using to show how our tasks work and test them. Let me quickly show it to you. So now, apart from just being able to run tasks, we can also measure the runtime, and we can also run all of them. So that kind of demonstrates also what I want to achieve is doing everything in Rust. I want to try to make stuff as fast as possible. So here you can see that for quite some tasks, we are running in millisecond range, microsecond range. Yes. And for others, a single millisecond, but for quite a lot, it's actually microseconds, which is pretty nice, I think. So I guess we can start reading the task 9 and see what awaits us. So, day 9, encoding error. With your neighbor happily enjoying their video game, you turn your attention to an open data port on the little screen in the seat in front of you. Though the port is non-standard, you manage to connect it to your computer through the clever use of several paper clips. Upon connection, the port outputs a series of numbers, your puzzle input. Your data appears to be encrypted with the Exchange Masking Addition System, XMAS, which conveniently for you is an old cipher with an important weakness. XMAS starts by transmitting a preamble of 25 numbers. After that, each number you receive should be the sum of any two of the 25 immediately previous numbers. The two numbers will have different values, and there might be more than one such pair. For example, suppose your preamble consists of the numbers 1 through 25 in a random order. To be valid, the next number must be the sum of two of those numbers. 26 would be a valid next number, as it could be 1 plus 25, or many other pairs like 2 and 24. 49 would be a valid next number, as it is the sum of 24 and 25. 100 would not be valid. No two of the previous 25 numbers sum to 100. 50 would also not be valid, although 25 appears in the previous 25 numbers. The two numbers in the pair must be different. Suppose the 26th number is 45 and the first number, no longer an option as it is more than 25 numbers ago, was 20. Now for the next number to be valid, this needs to be some pair of numbers among 1 to 19, 21 to 25, or 45 that add up to it. Okay. 26 would still be a valid next number as 1, and 25 is still within the previous 25 numbers. 65 would not be valid as no two of the available numbers sum to it. 64 and 66 would both be valid as they are the result of 19 plus 45 and 21 plus 45 respectively. Here is a large example which only considers the previous 5 numbers and has a preamble of length 5. Okay. In this example, after the 5-number preamble, almost every number in the sum of two of the previous two numbers. The only number that does not follow this rule is 127. So this, I guess, is 62 plus 40. Okay, I see. This is like 1, 2, 3, 4, 5. Okay. The first step of attacking the weakness in the XMAS data is to find the first number in the list after the preamble, which is not the sum of two of the 25 numbers before it. What is the first number that does not have this property? So preamble is always 25 numbers, right? Yes. Okay, and we have our puzzle input as typical, which is quite long, and numbers also are quite big. But okay, let's quickly create our typical stuff. So day 9 input, sample 9, which one do we want to use as sample? Let's use this one. Then we need a module. For those who are joining now, we are solving advent of code in Rust. We are solving day 9 now. Okay, no. And yeah, I'm doing some quick setup now, after which we will try to solve it for the sample input. So now we are doing D9. We also need to declare the module. I really need to automate this stuff. Actually, I can just copy this and do D9. We also have a REPL interface, and that's why I need to declare this stuff here, because then we will be able to call this. So we will do none, and we will do none here. Now, if we do our REPL thing, of course, it doesn't do anything yet, but we should be able to call it nonetheless. Yep, we got none, as you can see. And of course, we also will need to have some tests. So though this is advent of code, I enjoy also writing tests for this stuff, because then you can try to refactor things and make them look a bit nicer. Parser works. As usual, we need to parse stuff. Well, so let's start with parsing things. What will be our data? Our data is just a vector of U64s, right? Nothing fancy really. And input just reference to string. So what we do trim end as typical to not have the terminal blank line. Then we split by new lines. And then we map. For each of those, we have well, the line parse as U64. I will just do unwrap because I don't really care. Like if we get something wrong in the input, then we should fail. We shouldn't try to fix it in this case. And then we can just call collect. That I think is the easiest parser so far. So here in our tests, we need, of course, export everything from the containing module, and we need file system access. And then we can read sample input, which should be read to string, inputs sample 9, and then we also need to unwrap because it will return result, and then we can do parse sample input. We need to pass it as a reference, of course. Get numbers. So our first number should be 35. Well, we need to do assert equal. Our last number should be 576. You can do it like sum. And now we should be able to run it. And something breaks. What is, mismatch types. Why? Oh yeah, because of course it wants reference here. Okay. Okay, our parser works. Now we can start with trying to solve things. So what do we need to do? We essentially need to check that among 25 previous numbers, we have two numbers that sum up to the next number. I'm still trying to wrap my head about one thing. Do we need to have like moving window going through this list? I guess. Number is of the two previous. So preamble is different only in that we don't enforce the property. Otherwise, actually we can do hash set, I think. So like in this case, I think I'm actually thinking about trying to do it brute force that. We can try to do hash set and check for containment because we already did it in some of the previous days. We needed to, I think, some numbers to some specific thing. And then you can just look it up in a hash set, then take the current number minus the number you just looked up and look up this one. And then you just have two big O of one operations, which is quite fast. I guess let's also do, so I will extract a function here, which will be first how to call it, non-conforming. First, not some. First, non-conforming. Conforming. Gosh. And that will return, of course, option of U64. Input here will be vector of U64. For now, I will just say none. So our type definition already matches. And next, what do we need to do? So one thing. Yeah, and here we also will need to specify preamble length, which will be just usize, I guess. And then we just take a slice from preamble length till end. So all remaining numbers that we need to check. Does not follow this rule. And then we need to go, we I guess need to do like moving window of the, actually we can try to do like completely imperative there, right? So we can say start. So this will be like mutable start pointer, which will be, in this case, we initialize it to preamble length. Then we start maybe I can do iter and do something like window. Okay, I need to quickly look up this thing because I don't remember it. Do we have window and stuff here? Skip while position, product partition. I think we don't. Okay. And I think maybe in slicing, because remember I saw something like that. Yes. So returns an iterator over all contiguous windows of length. The window overlap. If the slice is shorter than size, the iterator returns no values. Ooh, that sounds cool. So RU, US, blah, blah, blah. Okay. So then we have this for current window. Essentially, we take the first window would be our preamble thing. And next window would be this. Then again. So eventually we also will need to track the amount of things we should discard from the beginning of it. But otherwise, that's kind of already simplified stuff for us. Okay, let's try to do it. So vectors are also slices. No. Okay, I have no clue. Okay, I have no clue what was that. My Visual Studio Code just went crazy for a second, and my OBS went away as well. Let me try to reopen it. This is weird. Sorry about that. So, okay, we're back in the game, I guess. I pressed some magical command that triggered like debugging mode, which is weird. Okay, fine. Yes, that's our day 9 thing. So let's toggle then mode. Okay. So we have input, and here we can make it into a slice, and then we get windows, and the size is preamble length. Okay. And then for let's also enumerate them. So we will get for index window in, and let's see what we actually got, because window, what don't you like? Windows. Okay, and if I do it without enumeration, well, worst case scenario, I can also just use Boolean logic, right? Slice window is not an iterator. Windows. Can I make it into iterator myself? No. Okay, this is strange. Oh, sorry. I completely forgot about my also switching my screen. Gosh. Okay, you can now see what I'm doing, hopefully. Yeah, I just tried to use this method for Windows, which for some strange reason doesn't really work. And I'm trying to get why it doesn't actually work. Because for me, it looks like it should. It should return, at least like if I look at the example. Is implemented for mute. Oh, I see. I wonder if, so like if I say, yes, okay, I got it. Okay, if I just consume it, will it work? It's not, because it wants mutable thing here, so I think mutable reference. No, it's declared as mutable. So I guess, okay, we got it. So now we got mutable thing here. I wonder why it needs to be mutable, because I don't see anything about it needing to actually mutate stuff. Fine. Okay, we started to debug stuff. Let's continue to debug stuff. Sample. Yeah, we can just do this here. We can take the let numbers, and then we can parse this stuff and got our mutable vector. Let's just set it to 5. And for now, I'm just debugging everything. I'm not doing anything more complex with that. So part 1 solved. And here we can do this. We say this is our sample input stuff. And we just solve it. And for now, I will do nothing with that. I will just use it to run stuff quickly. Numbers, of course. So yeah, we got those overlapping windows. .35 till 47, then we got 20 till 40. Okay, it works as you would expect, and ends up here. So looks good. Now we need to check. We need to add the things that we don't add, that we don't check the condition for preamble. So that's why I tried to do. I actually wonder if I still can do enumerate. Yeah, it seems to work now. And then say if index is larger than 0. So like we skip the preamble stuff. And no, that's not what I want to do. I want to make sure that when I go through this stuff, in input, I want to match it with, I want to have not only just windows with like numbers in this range, I want to also have the indices, so that I know that I don't check condition for the preamble. For new joiners, we are doing day 9 of Advent of Code. And yeah, we did the parsing, and now we try to use window iterators in Rust to solve this stuff. So I guess we can try to, I wonder, because I can say indexed input, and I can just create a new vector. Okay, that's a bit weird, because then can just take it like that. We don't need to try to do anything more complex. We can do iter, and we can do, so we can do into iter, and then we map it. Oh, sorry, enumerate it, and then we just collect it into another vector. And that will be a vector of indices with actual numbers. And then here, I don't need to enumerate anymore. I need to declare this stuff mutable. I need to use it instead of index. Expected slice found tuple. Yeah, we say elements, or like Actually, let's call it still window. So now if we execute it again, we will see that every element will have its index as well. So that, yeah, you can see, okay, it's a bit less readable now, but at least we got like 0, 1, 2, blah, blah, blah. So that we can filter out stuff that is in preamble and we can avoid checking if it satisfies this condition, because that essentially simplifies this thing. So like after 5 in this, or after 4 in this case, I can start checking stuff, but this like number can never be in my output for the first node conforming thing. Okay, so still, and we probably need to do it +1 here, because this way we will have like the last number will be the one we check against. Could be 1 + 25. 24 and 25. Would not be valid. Okay, I'm completely confused now by those windows. I think I will not do that. Instead, what I will do, I will try to just, I will go like completely brute force on that, because I don't want to spend too much time on this task, to be honest. Let's just do, okay, I actually still want to do this, because, do I want to do this? I don't think so. I think I can just then do for, yeah, in number in input into iter enumerate. So this is like each number now has its index, right? And then we can say if index is less than preamble length -1, then we just skip. It actually that's better. So if it's like preamble lengths or larger, then we do something. In this case, we then say, let's do it like lookup input clone. So we have like second vector. That I guess will be not super fun and super performance solution, but what can you do? If index larger than preamble length, then what we do, we take lookup, we take a slice of it where it's index -1, oh, actually everything before index, and index minus preamble length. So that's kinda right, something like that. So let's check if it makes sense what I'm just writing. Just run the test and see what will be our debug output. So first index is 5, as I expected, after the preamble. And the numbers we get are so like this is preamble. And our number is 40, I guess, right? It's also added here to make sure that we are doing something that makes sense. So yeah, exactly. So see number 40, that's our previous thing. Then the next one is 62. It starts 40 till 20. Okay, that's that's what I wanted to do with the whole thing, but that turned out to be easier to just clone stuff. And then we can essentially we can simplify stuff a bit, so we can use my hash set thing to avoid like complete quadratic thing, right? We can do std collections hash set again. Hash set is the star of this advent of code. I think I so far used it in almost every single day. So numbers to look up. Look up slice, which will be so we just collect it into a hash set. Yep. I wonder if this will work. Seems so. And then what we do, so look up slice. So for first number, for like x in so this is like complements that we need to save, right? Let's do found some. So if oh no, actually we can just do, so we look at each number that is in the set of numbers we can use to get the numbers that we have as sum of those two numbers. Y is just number minus x, so we know the second component. When we take each one number from the set we can use as the first component. And then if contains y, so if we found it, we know that we can just break, I guess. Can we break here? Yeah, I can break out of this loop because I found what I was looking for. Found, okay, let's say call it is sum. Let's make it false and let mute is sum, and then so that's kind of should be our solution, right? So attempted to subtract with overflow. Ooh. Number. Ah, yeah, because we use unsigned integers, of course. So so let's filter out x's that are larger than number. So x is, yeah. And let's try it again. Okay, we got 127. Is it correct? Oh yeah, it's correct solution. Okay, that's good. Yeah, we don't need mutability here. And we just can return this stuff, right? So let's still keep our test here for our sample input, which will be numbers, will be parse sample input. And then we just say first non-conforming numbers 5. And we assert equality that this is sum 127. The test should pass now. Something non-conforming. Oh yeah, sure. We map it, and here result as I64. And here for like actual solution first part, the preamble will be 25. Like our test now should pass. They do. And let's try to actually get our solution. Well, we can use our REPL interface for that. So we compiling and now we can do day 9. And that's our answer. Let's see. Yeah, we solved it. So continue to part 2. Gosh, I need a quick water refreshment, and we will read the part 2 task. So, yeah, before we read part 2, let's also make sure that we have this stuff here. Oops, I will just say assert, yeah, we read input, which will be then day 9. And then we just solve reference to input. And the answer was this, right? So it should be like that. And by the way, we are still quite fast. So we are like almost half a millisecond, which is a bit, it's a tad too much, but okay. That's all right, I guess, because we went a bit lazy. Okay, part 2. The final step in breaking the XMAS encryption relies on the invalid number you just found. You must find a contiguous set of at least 2 numbers in your list which sum to the invalid number from step 1. Again, consider the above example. So it's the same thing, right? Yes. In this list, adding up all of the numbers from 15 through 40 produces the invalid number from step 1, 127. Of course, the contiguous set of numbers in your actual list might be much longer. To find the encryption weakness, add together the smallest and largest numbers in this contiguous range. In this example, these are 15 and 47. Yes, producing 62. What is the encryption weakness in the XMAS encrypted list of numbers? The invalid number from step 1. Ooh. So this is interesting because we don't know the lengths of the stuff we need to find, right? We can definitely say, start with saying that weakness is this number and just hard code it. I think it will simplify stuff already. So we don't need to recalculate it again. But then what we need to do, like looking at this stuff, we essentially need to try like this and then this and then this and this and this and this and this until we overflowing essentially. And then we need to start with like next number, right? And do it again, I guess. I think this can be also kind of like dynamic programming thing, because if we check this range and then we check this range, they have overlapping substructure, right? So we know the sum of those already. But that will be more complex. I would rather prefer to start with brute force solution and then try to optimize it a bit if it is too slow. How many actual things we have here? We have like 1000 numbers. Okay, good thing we are using Rust, so even naive solution should be fast enough, I think. Last year I used Elixir. That would have been really a pain to try to brute force it with Elixir, but here I think it will be okay-ish. So what do? We take we again parse input. And then we do find just set contiguous set of nums. Gosh, I know this looks like a comically long name, but at least it is expressive to an extent. Yeah, we don't need this stuff. Actually, we can keep it. We pass the numbers and we pass the weakness, and that's kind of our function. The numbers will be, of course, still a vector, and weakness will be U64. And what we need to output, let's just output the vector of those things, right? So we actually can see what is happening. I will add debug already here. Oh, well, of course not sum, sorry, option, and of course not this, but this. So going with really dumb solution, we start with, we essentially have like indices, right? For start index in 0 till, I guess this will be like length -1, length -2, right? And then end index will be starting from start index to plus like 0, 1, plus 1 till numbers lengths -1. Actually, I wonder if I can, if it will remove parentheses here. No. Otherwise, we say none. So for now, I will just do debug and I will print that to verify that what I'm doing makes any sense. Yeah, I can compress those a bit so they are not annoying to look at. And here we can copy this and say part 2 solved. And let's say phi contagious blah blah blah. Sum to numbers 128 27 is the sample thing, right? Yeah. And here we'll just say debug for now. And we can try to run it and see what it will output. You should get like a lot of things here. Yep. So we start. Yeah, 0, 1, 0, 2, 0, 3, blah, blah, blah. Until we reach 0, 18. Yep. 0, 18, is it correct? So this is like 19, 18. Oh, sorry. This is 18 actually, because our, yeah, okay. Length -1, then 1, 2, 1, 3, blah, blah, blah. Okay, looks correct to me. And the end is 17, 18. And then what we just need to do, we just need to sum all the numbers, right, in this interval. So sadly in Rust, yeah, I'm thinking I will probably get some exception because of that, but can I do sum? Can I do fold? And if I do it like that, I cannot sum slice? That's so weird. Well, we can always do like iter. Can at least some stuff here. Or actually, let's do it like that. So von x in I will just go completely imperative now. Sum equals 0. X, and if sum equals to weakness, we just take this stuff again, and we copy from slice. What to do? Copy some. Okay, no, that's not what I want. I want to just do into iter, and then I want to collect this vector. And then I will return this thing. Found reference. Oh yeah, I don't need the reference here. Vector found struct. Okay. So let's see how painfully slow this will be. But at least we are correct. We found the region. Then the only thing that we need to do apart from that, so this is our region. We can do if let some region and here then we need to, I wonder if it can do max. So region is, oh, sorry, dump. Of course, we need to do it in the second thing. So here, we can do then region iter. Region is a vector, yes. Iter. No. Sure. Oh, it already has max. Okay, not correct one. Max. Returns the maximum element of an iterator. So we need to find maximum and minimum, right? Smallest and largest number in this contiguous range. We need to add them together. So region iter min. Okay, this is so inefficient, but fine. And then we just do sum, or actually we don't even need to do much, right? We can just do if let sum largest, smallest, sum largest, sum smallest, and this is of course inside a tuple. And then we just return sum largest plus smallest. And that we cast to I64 because that's what I need to return to use it in the REPL. Okay, so now we can finally convert this for new joiners. We are solving Advent of Code. This is day 9. We are almost done with the second part, but then we will be solving day 10. Yeah. So fun only starts. What is our... We expect to find 62 here, right? Yep. Solve to numbers. Oh, I cannot actually test it like that, right? Well, we already kind of tested it, so I guess we can just comment it out. We know that it will return correct region. What we care about now is that this stuff will actually work. Let's make it fail here in test for now. We can try our REPL again and try to run it manually. So day 9, part 2. Okay, this is so far the slowest of all the things that I did, but we got some answer. And let's see. Well, brute force actually worked this time. Not the most beautiful algorithm, but we solved it, and we can change that. And then we can just make sure that all our tests pass. And then we can start with part 10. So, part 10. Adapter array. Patched into the aircraft data port, you discover weather forecast of a massive tropical storm. Before you can figure out whether it will impact your vacation plans, however, your device suddenly turns off. Its battery is dead. You'll need to plug it in. There's only one problem. The charging outlet near your seat produces the wrong number of jolts. Always prepare to make a list of all of the joltage adapters in your bag. Each of your joltage adapters is rated for a specific output joltage, your puzzle input. Any given adapter can take an input 1, 2, or 3 jolts lower than its rating and still produce its rated output joltage. In addition, your device has a built-in joltage adapter rated for 3 jolts higher than the highest rated adapter in your bag. If your adapter lists were 3, 9, and 6, your device built-in adapter would be rated for 12 jolts. Treat the charging outlet near your seat as having an effective joltage rating of 0. Since you have some time to kill, you might as well test all of your adapters. You wouldn't want to get to your resort and realize you can't even charge your device. If you use every adapter in your bag at once, what is the distribution of joltage differences between the charging outlets, the adapters, and your device? For example, suppose that in your bag you have adapters with the following joltage ratings. blah, 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 blah. With these adapters, your device's built-in voltage adapter would be rated for 19 plus 3 equal 22 jolts, 3 higher than the highest rated adapter, so that's the highest rated one. Because adapters can only connect to a source 3 jolts lower than its rating, in order to use every adapter, you'd need to choose them like this. The charging outlet has an effective rating of 0 jolts, so the only adapters that could connect to it directly would need to have a voltage rating of 1, 2, or 3. Of this, only one you have is an adapter rated 1 jolt, difference 1, so this one. From your 1 jolt rated adapter, the only choice is your 4 jolt rated adapter, difference of 3. Yep. From the 4 jolt, 5 jolt, difference of 1. The adapters rated 5, 6, or 7 are valid choices. However, in order to not skip any adapters, you have to pick the adapter rated 5 jolts. Okay, that's important actually. And then I guess next choices will be 6 and 7. The only adapter that works with the 7 jolt rated adapter is the one rated 10 jolts, difference of 3. From 10, the choices are 11 or 12. Choose 11, difference of 1, and then 12, difference of 1. After 12, only valid has a rating of 15, then 16, then 19. Finally, your device's built-in adapter is always 3 higher than the highest adapter, so its rating is 25 jolts, always a difference of 3. In this example, when using every adapter, there are 7 differences of 1 jolts and 5 differences of 3 jolts. Okay, here's a larger example. In this example, in a chain that uses all of the adapters, there are 22 differences of 1 jolt and 10 differences of 3 jolts. Find the chain that uses all of your adapters to connect the charging outlet to your device's built-in adapter and count the voltage difference between the charging outlets, the adapters, and your device. What is the number of 1 jolt differences multiplied by the number of 3 jolt differences? Oh God. Must admit, I don't really enjoy those tasks when you need to count stuff, but okay, today is this kind of day, so we just solved day 9, which is all about counting things and summing them. Now we have another task that is also summing stuff, but let's solve it anyways. So what we will need to do, I think this time I will even skip on sample input because I think it sounds pretty simple, at least, well, how I read it right now. We parse the list as usual. I probably need to extract helper function for that because there will be more of like number lists coming our way anyways. Then we sort it and then we just, we go through it, finding the next smallest one, like 1, 2, 3 thingy. We probably can also optimize it with hash set if we want to make it a bit faster, but we probably won't need to. So sounds quite simple. Yeah, and input is actually quite small. So we do our typical ritual. We add the stuff for our REPL. Sadly, I was not able to find a nice way of auto-generating this thing in Rust. There seemed to be a compiler interface, but it's not like officially supported, so not as easy to use. Let's do this. Let's do that. So I think I'm already so automatic in doing that. So I know that we will need that. I know that we will need a test. Well, we don't, I wouldn't even write a test for our parser here because I think it's quite simple and we did it so many times already. So we can just do this. We can quickly create a parser function. Actually, we can like literally just copy this stuff, right? That's our parser function. So yeah, let's open day 10 just to make sure. Here we can at first just do parse input, right? Then using our REPL, we can verify that it was parsed correctly. So just building it. Yeah, you can see we got all the numbers here. So 111 to 65. Yep. And what do we need to do next? So we need to count what is the number of the 1 joule differences multiplied by the number of 3 joule differences. We essentially need to write a function which returns a list of differences, right? Joule differences. So joule address is a vector of U64, and we return a vector of U64 too, for simplicity. Now, can we actually modify this stuff? Let's just sort it, I guess. Yeah, it sorts it in ascending order. And then, well, for now we do it like that. Then we will have mutable starting voltage, which will be 0. Actually, I don't even want to sort it, I guess. What I want to do, I want to just put it into a hash set. That I think will be more than enough here. I then can remove stuff from there, right? I can just do hash set. We can then do, because order doesn't really matter at all here. Available. Or we can actually just call it voltages as well. We do voltages into iter, and we collect it to a hash set. So, and then let's call it current voltage. And then for what is our termination thing? Once we exhausted everything, right? Let result. This will be an empty vector. Then while voltages is empty, let's not empty. Oh, that's actually adapters. I'm dumb. Adapters. Yes. So we got our adapters, and what we do next? So for current, we can only do like 1 plus 2 plus or 3 plus. That will be not very beautiful code again, but we can just say if so essentially we always start with the smaller one, right? Then result push 1 current equals oh yeah. So yeah, of course it wants reference here, I guess. Yeah, it's yeah, hash set of U64. And here it probably also wants reference. Cannot borrow as it is not declared as mutable. Of course we will declare it as mutable, why not? And then we just do this. So essentially, else if contains current to, push to, push 3. And if something doesn't work here, we will just panic. Impossible adaptation. Impossible voltage difference. Right? So we did that. Remove current. So we always push this stuff, and when devices, then the highest adapter. So when we take 3, we remove the last one, and then we need to also add 1. So result push is always 3, right? And then we just return result. And that should be solution of part 1, in principle, if I understand it correctly. So adapters. And then what do we need to do? We need to, what is the number of 1 joule differences multiplied by the number of 3 joule differences? So 1 joule difference multiplied by number of 3 joule differences. So differences iter filter, it will be joule is equal to 1. And we just need to take count of that. And for 3, we just change the number here. And then we just return sum once it's multiplied by 3, this count. And we need to cast it to i64 to satisfy our REPL. Yep. It probably, yeah, it cannot compare. This is like too much references for it. So now it's not too much references anymore. And I guess I will really try to YOLO it now. So let's see. Oh, actually, one thing how we can very quickly test it. We can replace our input here with our sample. And then we can just write this 220 and 10. So yeah, that looks correct to me. And then we can just revert back. I think that's the bigger one. Yes. Yep. And then we can execute it, and we got our number. Let's see if it's correct result. Yep, it is. Okay. So shall we do test? Let's do a quick test. And last part for day 10, the second part for day 10. Part 1 solved. So that's the result. I will just copy this stuff from here. Let's see that it passes. Yep, it does. And now part 2. To completely determine whether you have enough adapters, you'll need to figure out how many different ways they can be arranged. Every arrangement needs to be to connect the charging outlet to your device. The previous rules about when adapters can successfully connect still apply. The first example above, the one that starts with 16, 10, and 15, supports the following arrangements. Oh, that is interesting. 1, 4, 5, 6, 7, 10, 11, 12, 15, 16, 19, 22. This is like the original thing, right? And what happens here? We remove one and we instead we get this. Then we can get 10, 11, 12. So here we remove another one. 5, 7. We remove 6 and we remove 11. Oh, I think I start to see a pattern here. 1, 4. Here we remove 5 as well. Then we can remove, of course, 6 as well, yes. And then 10. So, like, I think the original arrangement is always the longest one, right? Because we took all the adapters. We cannot switch the order because that would break the rules that are still applying. So, like, next one should be 1, 2, or 3 jolts, higher. So then we just need to remove stuff, essentially. The charging outlet and your device's built-in adapter are shown in parentheses. Given the adapters from the first example, the total number of arrangements that connect the charging outlet to your device is 8. 1, 2, 3, 4, 5, 6, 7, 8. Yes. The second example has many arrangements. Here are a few. The one starts with 28, 33, 18. Oh wow. You glance back down at your bag and try to remember why you brought so many adapters. There must be more than 1 trillion valid ways to arrange them. Surely there must be an efficient way to count the arrangements. What is the total number of distinct ways you can arrange the adapters to connect the charging outlet to your device? Does it kind of says to us that that we won't be able to brute force it, I guess? But this is really. So like here, let's see how many lines we got. 112. Which is the total number of distinct ways you can arrange the adapters to connect the charging outlet to your device. So we need to count those ways. But that is... I actually don't buy it. I don't think we will have like more than 1 trillion valid ways to arrange them. How did we even get this 19200? Because okay, I see. Because we still even if we cannot switch stuff, we still can like remove a lot of things, right? Can we whoa. Okay, that may be the first task I fail. But shall we still try to do it, I guess? Because like essentially every time we remove a number, we get another number. We kind of get like one branch, right? Then we remove another number, we get another branch. And then we can, in essence, converge eventually with them, I guess. Is arrangement. Because how do you count this stuff? You can try to move it. You can try to move through the list, right, and see which one number you can remove. Because all of those like hard arrangements, they start with you removing one number. Then for each of those, it says more than 1 trillion valid ways to arrange them. how long it will take for us to calculate 1 trillion things. I guess quite long. Supports the following thing. Should I even attempt to write a brute force solution here? Will it be a complete waste of time? I'm not sure. But this is also, like, there should be some way to do it. I think this is definitely dynamic programming thing where, hello, where we can when do you choose Elixir Phoenix and when Rust? Well, Elixir Phoenix is definitely a language and framework better suited for web development, right? So Elixir is generally a good high-level language. I solved Advent of Code last year with it. In case of Rust, I'm learning it, still a bit of production code with it already, but I still feel like a beginner quite often. It has way better performance. It also has static type system. So if you really need to do something very fast, process a very large amount of data, or you writing something that is super, super critical for you and it should fail as little as possible, then Rust probably would be a good choice. Or if you're doing something embedded, then Rust is a good choice. Otherwise, Elixir is typically faster and easier to write. I hope I answered your question. Yeah, let's try to do dynamic programming there. So we have parser, we have those jolt differences. Jolt differences, good thing that we extracted this function because that will be our input here, right? So that stuff happens here. Now, next step would be to essentially go through them. Like we probably need to have like matrix of numbers that we remove. So we can set up something like oh, no, it's not even jolt differences, right? I'm going crazy. This is more like, because here we only push this stuff. Here we actually need to get the adapters themselves. Or not. I'm so dumb. If we try to okay. Because if you have jolt differences, does it help us or does it not help us? Like the first part asked us to do that, and I feel that that was for a reason. Like here, oh yeah, I think it did it for a reason. Because if you have 3 and stuff, then we know that we can look for 2, but we still need to have it like with our numbers, right? Like essentially 3 and 2 are candidates for removal, I guess. Does it work like that? Like if we have 1, we can also, no, I don't see how it helps us. I'm thinking, what else can we try to do that? How can we represent those removals of things efficiently? We can try to do something like a matrix. No. Can we just try to brute force the first part? I think that will be simpler because I think I'm also overthinking it a bit right now. So we got adapters, we got differences. Let's also create a function that infers. So reconstruct sequence, right? which takes jolt differences and creates a new vector with actual adapters. Let's call it reconstruct arrangement maybe. So we can just like fold this stuff, right? We start with 0. And in this case, we ignore like 0 and 22. We just do like this stuff, right? We only need this part of the vector. So we will then have a function that takes accumulator and element. Actually, 0 and empty vector. Current result. And then current will be current plus jolts. So this is like our difference and result, or actually result we can just push to it. We don't need to do this that way. We can simplify it a bit. That this is empty vector and current is that, and then we result push current, and then we proceed with current. Doesn't like it because I guess jolts, yes, it's reference. Why is that? So first is init, and then it's a function where it takes current and then it gets jolts. Oh yeah, because of course we need to return result here. Okay. So we can then do let arrangement, and then we can do reconstruct arrangement from differences. And then we, for now, just do debug of that to see if we did it correctly. Differences. Yep, we can use reference here. And yeah, I guess we actually will need to do the sample stuff, right? Because otherwise it probably will be too slow already. So sample 10. And we just take the first one, so the really small one, to make sure that our very naive solution works. And let's just call it part 2. I don't want to get the whole big failure message, so I'm writing none here. So we got our arrangement. Let's see if it is correct. 1, 4, 5, 6, 7, 10, 11, 12, 15, 16, 19, 22. Also, the last one we need to remove because we don't care about that one. So you just say result length -1, right? And now if we try it again, we should get all the same stuff, but without 22. Yeah, okay. So we can reconstruct stuff. So now we need to figure out how we can count those arrangements. I guess we need to see if we have a number. Okay, let's try to just do again brute force. Right, where we have, this is, yeah. Init, which will be we can use reference here. I want to first try to generate them actually. I'm not sure that we really need it, but at least we can try. And here, so we don't use this one, right? We got it as an input and we need to generate once we have like one number less and then like another number less, etc., etc. How do we do that? We need to find a number that can be removed. That's the only thing, right? So we just need to go for and then we cannot remove first or last, right? So if index is not and index is not init length -1, then what is the condition for removing number? Here, for example, let's look at this example. So we take this as an input, this one, and we get this one. Why can we remove 6? Because the difference between 4 and 7 is 3. So if difference between the previous and next number is less or equal than 3, then we can remove a number. And init index -1 plus, I will extract it into an inner if condition just for clarity, plus init index +1 less or equal to 3. Then we can remove the number. And then we can essentially say init clone remove let mod arrangement. That will be super slow, of course, for bigger one, but remove index. Do we even care about them? I'm not sure. I think we can just avoid it then. Remove index. And then what do we do? Yeah, we just return it. right? That will be a vector, mutable vector, and we just push stuff there. So we take this arrangement and then we say arrangements, push arrangement. And in the end, we just return arrangements. Yeah, we forgot enumerate here, of course. So let's try to run it. And see what happens. It returns empty list, empty vector. Okay, interesting. Oh, I'm dumb. So we always need to take, yeah, we need to switch it here. So next number minus previous number should be less equal. Okay, that makes sense. So we start with our original arrangement, which is from 1 to 19. Makes sense. Then we get 1, 4, 6, 7, 10, 11, 12, 15, 16, 19, 1, 4, 5, 7. So 6, 7, 5, 7. So we got 3 like with one number removed, and then we need to apply the stuff recursively, right? So we take this stuff, arrangements, push. Actually, we can even make it a bit simpler. So we can then say dot reserve retain, essentially. But here, of course, we'll need to change to reference first. So that, yeah. Let's see if that still works. Yep, seems so. So here then we can do this, and then we can derived arrangements. And then we can just move stuff here, right? So we can say append derived. And here that will be mutable. And this, of course. Found struct. Yeah, let's make it a mutable reference. And then after that we can push our thing. So push arrangement. Okay, let's try to run it again and see if we got all 8 now. 1, 2, 3, 4. So 1, 4, 7, 10, 12, 15, 16, 19. That's the shortest one. Okay, I lost count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh yeah, so we got more because some of those are already there, right? So that's kind of shows us that we have overlapping structure, which is typically a thing that tells us that we have dynamic programming problem. which is funny. Do we actually want to, let's say, like, what do we need to do? We need to save the number. Okay, I need to look up into article because I haven't done dynamic programming for so long. Let me find it. Gosh. So that's the thing, I guess. No. So top-down approach. I think must be small. So let me make it a bit bigger. Problems. Okay. So we can use memoization for that, right? Overlapping memoizes this. So, okay, let's try to do it. We can. I wonder how we can check that we counted this stuff. So it in essence, we only need to return the number. We don't need to return the vectors themselves. So we can try to create like a global hash table. Let's go with counts. I will even give it a type just for simplicity. So what do we map then? Do we want to use the whole vector? I guess we don't. We just want to check if we have enough, like for each of the arrangement, we map them to. Maybe for like, we can, like the number of removed elements is lower. We can pass around vectors with like removed elements. Yeah, I guess so. So we will have like a vector of u64, which like the elements we removed so far, mapping to the number of arrangements there that you can still make, I guess. And then we will have like empty vector, which will be our answer, I think. By the way, even before that, let's quickly look what happens. So if I run it via my REPL, oh yeah, that's the answer for the first thing, I guess, or no? So it does like arrangement, and then it needs to run make arrangement, right? And transfer so long. Oh wow, is it for real? But stop, how how did that happen? Because in test, Because we are using the whole input. Okay, now I understand it here, because that's too long and that's why it's so slow. So instead, we can of course do d2 and then say sample 10, so that, yeah, but still it's ready for, you can see that we got, it's not yet unified even. Okay, let's do then mutable counts. And for those mutables, them into make arrangements. And here we need to change our logic a bit. So I will just take this stuff and I put it here, just call it make arrangements dump, so that we can refer to this logic while we're writing our new fancy thing. Yeah. Here we have a number of things happening, so we don't need to push this stuff. Instead, we will return nothing, really. Don't push stuff into the vector. So if we know that we can remove the number, and we also will need to have like the numbers we already removed. Thomas, don't make fun of me yet. I was trying to fix Kafka now, but it's good that you solved it. I guess this is, by the way, the moment when I really miss Elixir, because I could have just memorized the thing without trying to think about all the mutability and recursion. But okay. Okay, what do? We take this stuff, we remove the index. We actually don't want to, I guess, clone this thing and remove stuff. We just want to accept an additional parameter. Yeah, it is like its complexity escalates so much, especially I guess by day 15 it will become crazier. I'm really glad that I will soon go on vacation, so I will have more time to solve those things. Otherwise I wouldn't be able to keep it up. I think solving 2 tasks every 2 days is quite crazy. But yeah, init. We just need to take a number of things that we already removed, right? So this will be like removed vector of U64. Yeah, while having full-time job is very tough. And I'm not even trying to compete in leaderboard, because I don't understand how people can do it. Like if you try to wake up also every morning in Europe, it's at like 6 or 7 or something, then you go crazy, I think. So if you have a vector of remove things, then what we need to do in counts, we check if counts. Can we do, oh yeah, we can do entry with the vector, which will be removed stuff. And then we can look at if it doesn't have the thing, do we need to count it? I guess, oh no, I'm dumb. Let's go to let new removed. Which will be removed clone, and I will just do it mutable. Oh god, it looks so ugly. New removed, push init index. Oh, actually I already selected it, so I can just do num, avoiding one lookup. Hi, Hassan. And what do we do here? We have now new stuff plus one element. We, instead of that thing, we now know that we found one more, right? We found one more, so we can then say counts entry new removed. It will probably want a reference here, and if it exists, we do nothing, I guess. Or we insert. Will we always have like no. I'm making it more complex for myself. I should just use the plain map API. So I will do because instead I will do if we will match counts get things that are already removed. I think we even can do like unwrap here because that is guaranteed because we already have it removed, right? So we already counted that. Yeah. So previous count, and then we just say, and yeah, we get the new removed, and then we say counts insert. And I guess I'm also missing like I need to do it for like previous things, add one, but I can do it as another step, I guess. So we insert new removed, and we say that will be, I'm not sure that I'm counting in correct direction, I will say, but for now, let's just try to do it and see what happens. Probably nothing good. Found, yeah, we can dereference. Here, removed. Yeah. And this, yeah, it wants to have a reference, of course. Since I'm cloning removed, I can as well pass reference, which will be cheaper than pushing the whole vector on a stack. Yeah. So we will get some, yeah, and of course here vector will be empty. But now I'm missing one important thing. Sure. Which is, I don't do the recursive call, right? So I just need to do it here, I guess. Counts init new removed. Oh god, that looks so weird. Yeah, because that thing is already gone. So I need to actually do clone here. Yeah. So that's my recursive call, and I probably will get some complete nonsense right now. What can you do? So I know that arrangements is correct. I just need to do, instead of doing that stuff, I can do counts, right? Right. It probably still, yeah, that thing will annoy me a bit, so I will do this, and I will do just comment it out, so it doesn't print every time I try to run it. And here I'm using sample input, so it should be all right. Cannot borrow count because it is borrow. Why does it say that it's warning? Oh, option unwrap. So that's I think I really do it like in wrong direction, right? But okay. we do this, and if we have some previous count, we can do this stuff. And if we get this, oh, that looks so incorrect, but I'll just say, for now, the simplest solution, we'll say 0 here, just because I know that it's probably not correct, but it's overflowed, it's stuck. Of course it did. So I can, of course, make it non-recursive, but that it just feels kind of incorrect. It feels like, so what I'm doing, like I start with my whole thing. My removed is empty at this point. So it's none, and I say 0, which makes sense. But then I clone it. I push my numbers that I found. So for example, in this case, I will push 11. For example, if we execute in this order, doesn't matter, because order can be arbitrary, I think. And then we insert 1 for this thing, which is already incorrect, right? Because we only need to insert stuff when we found that we cannot remove anything anymore. Gosh. Oh, my brain. I think, can we somehow revert it? I'm just trying to look at the simpler function because that may be a bit nicer when you think about how to solve this kind of stuff. So when we push this remove number and we call ourselves recursively, oh god, the only thing that I did for removed is counts init for init. Oh god, no, it won't work like that. Because init never becomes less, right? I need still to remove stuff from init. Yikes. Well, I'm not sure that all this cloning will help me really. New init. But what can you do? Do new init. Parse it. So because I wasn't actually doing any proper recursive descent here, or, well, not really recursive descent, but some kind of collapse into something useful in the end. So let's see. Found reference. Okay, let's try again. Okay, we got something, so at least now it terminates. It doesn't look very useful yet. So like if we remove 6, Does it even put like empty list here? No, it doesn't. No, that doesn't make yet much sense, but we started to get somewhere, I think. So I'm not sure that my idea with counting removed stuff makes much sense. Maybe, but otherwise, how do I look up previous state? So like, if I have my, okay, let's try to put it somewhere graphically because I think that will make it easier to think. So that is my original input. My hash map then will be, right? Nothing removed, one arrangement. Then we remove one number that in this case is 11, which my map then shows as one. But this I also need to update to 2, right? Because now I found one additional thing. So for each of the ones I find, I need to update the ones with less elements, I guess. Then I have this stuff, which 11, 10, 6, but still contains 11, right? Yes. Let's imagine that we somehow did it. So that becomes 1 and this becomes 3 now. I want to quickly finish this example so that I know what I need to actually replicate in my code. So here we have 11 removed. So $11 and $6 actually. One. Right? So after this one, we get this one, which will be so my general idea is that I want to build a hash map where actually one thing I'm not sure that what I'm doing makes any sense right now. It's just a guess, but I think like if I know the counts, for example, for all 1 removals, and then I start with like 2 removals, then I can just like do +1 on them on a hash map where I save my counts, but then I actually need to go into backwards order, right? I need to start with the most removed stuff. Then I know that I have like 1 possible solution there. Then if I add back to it, it will be 2 or something. In that is that we arrive at the same perturbations of those things when we try to remove 1 number. Like, and then call ourselves recursively, remove another number, and then we have kind of like similar lists appearing multiple times, which shows that they have the same structure, which shows that if we have a hash table that maps the removed elements with the count of things that like possible after that step, we can save on computation. I don't know if it makes any sense, but that's kind of possible solution here, I think. I still need to figure out the order, right, in which it happens. Okay, so it makes at least some sense, I guess. Not sure how much. I feel that I'm doing it in the wrong direction, and I feel that I'm also missing something here, because let's try to finish, I guess, this unwrapping, because then I will see the states that I want to build and if it makes sense or not. So here we also removed 5, I think. We actually just, I think, removed 5 here, right? 5, 6, yeah, we just removed 5. So this is like one removal. Okay, it makes sense, but I won't spoil. Okay. Okay, at least I'm onto something, I think. And then, like, the tricky part here is then I need to update this then, right? Because we already found 5. And then I need to do this. What do they remove here? They removed, like, I can copy that. And they have 5, 6, 7. And they also removed 11, so 5 and 11. And here, actually, I then need to say, so like, next step, I need to update that to 2. And that I need to update also to 2, I guess. And that I need to update to 6. Okay. Because then in principle, like 5 and 11 is 1, 1 plus 1, 2. Doesn't make any sense. Not sure. Now 1, 4, 7. Yeah, we have this where we added 5. And now we also removed 6. Yeah, I feel that it probably will. So the thing then is we need to somehow do it in reverse order. But I'm not sure how to count them in reverse order, because if I go in reverse order, that makes even less sense, to be honest. But let's try to see if it makes sense here. 5. So of course, I now will like very artificially arrive at the answer. Actually, did I start with... Oh wow, no, I actually don't even arrive at correct answer this way. Okay, that at least tells me that I'm doing something. Ah, no, that should be 7. I'm dumb. So here I should get 8, and then I also removed 11, right? But now look, if I try to normalize this thing, so this is like 1. This is like subsequence, it's 2. This is also subsequence of that, it's 2. This is 5, so 1, 2, 3 of those. This is 6, 11, which is 2. Actually, this is 4 even. And this is 12, which is 1. And this is 11, which is 11, 4. Okay. Yeah. 4, 1. But it still doesn't make much sense, does it? Because then I have like all my 1 element things. And they don't even sum to anything here. Yeah. But I cannot use, like, now I understand that it won't work this way, because I cannot use easily results of my previous computation here. So like for 511, like this doesn't make sense. But that's how I will arrive at the result. Like in principle, of course, we can try to look at it in another way. So if I look just of those like removals that I have, then we will have this kind of stuff here. Gosh. And then, so like, if I try to map them in another order, if I start with this one and say that this is 1, nah, doesn't make still sense. Because I'm just thinking about it as branches of a tree that kind of converge to something. So like this is created from this one, which is created from 5. And this are created from 11. So and then we have 12, which is 1. And then this should in principle be equal like 3, 6, 7 plus 1 for itself. So that will be 1 plus 1 plus 3 plus 3, which true. If I list all removed, it is the same as listing all reminders. They're probably just shorter. True, I'm thinking about that now, because then I think I may arrive at more natural recursive solution, right? Because here the problem will be also like computing, like getting back there and stuff. It will be rather annoying. Instead, but like operating reminders will be also usually a bit tougher. At the same time, it's the same thing, right? So like it doesn't really matter. We can take reminders. The only thing that we then, oh, okay, you're right about one thing. I wouldn't need to pass additional list, which will make it simpler for me to track. And I guess my brain will blow up a bit less. But I still will need to update stuff. I still will need to somehow go back and update it. Okay, let's try to not do removals. Let's try to do the stuff that we actually get here. So reminders. And in principle, what I can do, I can take the third version of this function and make arrangements node dump. And I can take my counts. My counts would be still the same, right? It doesn't really matter. But then for arrangements, yeah, we can then recreate derived thing. But then we still need to, and we can then counts. If we arrived at the same thing, we shouldn't even consider it, right? We can then do counts. You shouldn't try to return anything from this function. So we can remove this stuff. We can take init. And then we can do and insert. For now, I will just insert it unconditionally. I think it doesn't matter really if we do double insertions. And for now, I will just set it to 1. And then derived make arrangement. And then for that, oh, and then I actually can try to do it properly, saying, okay, I can just do a check here. Oh God, of course. So like if, okay, recursion 101, obviously, if you get count of init, actually you can do much. So if it's sum x, we return x. That is the thing then. We return something, but not what I originally tried to return. And then if we don't have it, then we go the whole calculation road. Like, okay, for now I'll just write 0 there, so it doesn't found. Yeah, sure. Make it like that. Yeah, it's satisfied. So then for each of those, we do the same thing. If we can remove, we remove. And then we for each of the count arrangements, so answer for this thing will be this plus 1, right? Gosh. So, and of course we need to do, okay, let's say derived count, so it's a bit nicer looking. Count arrangements. Gosh, I think that's actually the solution. Or no? What don't you like? Oh yeah, sure. What don't you like still? Derived count if I and if nothing happens here. Arrangement. We need to. Oh, we still need to do a vector, I guess. Counts. And then almost there. Found struct. Oh yeah. Local counts. Local counts. Local counts. Naming is not the best, but okay, that looks better. Counts arrangement. Okay, third argument is not needed anymore. And arrangement is, yeah, we can pass reference here. So let's see if we actually did it. Yay, it seems that we did something. Yeah, for our original thing, we got. Oh, the only things that we 1, 4, 5, 7, 10. Like, we still count duplicates, right? 10, 12, 15, 16, 19. So the only thing count duplicates, and that is kind of a thing. Init count iter sum. We need to push it here, I guess, right? To the arrangement. Do I do it correctly actually? I think I need to only do it here. Counts. Let result. Because this is finalized. Right? Right. So for init we pass result. And of course found reference, sure. Previously remove. Left from the position we previously removed. It means that I can order the recursion thing so that I don't actually get duplicates. That makes sense. But let's see, because I think that should also work. Because here I only push like fuck at least. So oh okay, 147. Oh, +1, I believe. I forgot to. Push derived count. E. Don't remove left as a position. Shit, my brain is melting already. Why do I get zeros here? So we have derived count for arrangement that should insert it for itself. How do you even get 0 inserted here? Like if we init clone result. I guess that should be +1 for the original thing, I guess. Yeah, it's just guessing by now. Oh, type annotation needs needed. Gosh, I think that should satisfy too. No, I'm still counting doubles. I guess I need to actually do the ordering, which is a bit annoying. Okay, that stuff I can actually remove because that was definitely wrong. So then to count arrangement, derived count. Or actually, that is, yeah, so this is my original list, right? 1, 4, 5, 6, 7, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 5, 6, 7, 15, 16, 19. So yeah, okay, now I count everything. I need to make sure that I don't insert something, right? So where do we insert stuff? Arrangement. I need to only do it. I actually can just try to switch to entry, right? Because then I will have it. Can I get to the same thing multiple times? I guess so. Should I visualize it? Do I want to? Not sure. So definitely we shouldn't insert if you already have something there, I guess. So we do count entry, counts entry to arrangement. And then I think in entry. Oh no. I will just do if node contains. So contains key. Yeah, I think so. I think I will go through it every time, but I think if I don't count the same thing multiple times, it should be correct. Like I should just, reference here. So that can prevent already us counting the same thing multiple times, I think. Node contains key arrangement. If, and here, of course, I can also do it the same thing. Actually, here I know that that is not possible, right? I cannot insert it before I arrive at this point. So that should be okay. I still will get overlapping thing, I think. Or do I? 1, 4, 5, 6. It seems that actually I solved it finally. Yeah, okay. That if condition was needed. So let's do last debug, which will be counts get arrangement. Reference, of course. So now we should get 8. Gosh, that took me, how much time it took me? I think like 40, no, more than 40 minutes. Like almost an hour, I think. Gosh, I'm becoming old. But okay, it seems that it finally works. So we can then say that this is our answer. Right? Then, of course, we need to still map it. Oh, I'm not done, I guess. Okay. Okay, if I will not be done in like 15 minutes, I think I will give up for today. Because point is not torturing myself, but let's see. Yeah, sure. So we got this. Oh, I broke something. Yeah, because I said none, of course. It's sum 8. Okay. Shall we try this sample that is a bit larger? Part 2 samples solved. I want to separate those tests, so I don't need to do it. So, okay. Let's do sample 10.2. Here is a longer example. Sure. So we got our longer example, and now we can try to call this thing again. Sample 10.2. And our answer should be this. Gosh. It probably won't be that, right? Oh. Whoa. Okay, so it's even more actually. Distinct arrangements. Should I be like completely crazy and create another hash map with like, or like not even hash map, I can create a hash set where I put like a hash of the things in my arrangement to speed it up a bit. Yeah, it's a lot. I really wonder. I guess I still count in the stuff that is overlapping, because I can remove like different numbers, right? And then like arrive at the same point multiple times. But I still don't understand how it happens, because this is like derived count. Maybe I'm... So if that returns 1... Arrangement. I think I'm also adding too much ones, actually. I think that should be... That I think is not needed. I think if I'm not... I will probably fail with my first one. Oh no, first one still works. Okay. So should it then be the same arrangements? Yeah, I'm thinking why then? But okay, my first part still works even if I remove that one. So that was definitely wrong, but I end up also with the same number. What? It is interesting. Do I really end up still with the same number? Yeah, I still do. 2010 local counts push. Because what is the logical thing here? What's the logical meaning behind that number in the counts map? This is number of derived arrangements from the arrangement. So we have local counts. So like, I think that's the problem here. We take those local counts and we push them there. We just take the number, but they can end up with the same thing. Another thing that they can end up, yeah, and that can also happen recursively. Can I just, can I make this stuff also like a hash map? Because if I'm making it a vector, then I guess I can count stuff multiple times there. Yup. Okay. Local counts. Okay, I will try to do it like that. I will take this stuff and I will also copy it again, because otherwise I may regret what I'm doing. The entries in counts. Count the entries in counts. Actually, that makes sense. But I wonder, let's try it, because that's a very simple thing to try, right? We can try to count them. So keys, and then we say lengths, and then we say, right? Let's see what happens. So now I'm not arriving at all. At all of those, which is fascinating. Counts. Well, get. But that is a good idea. That should be simpler, right? First test is still correct. Like, it's always correct so far, no matter what I do with this code. I will move this count arrangements to somewhere else. That's our new backup. when you're too lazy to use git. So we are missing some keys, which also doesn't make much sense. I'm not getting how I can actually miss stuff here. Oh, but then it will, like the thing is, if I'm still collecting everything, then I will definitely fail on the bigger input, right? So that kind of sucks. So we get this. Yep. Yeah, it doesn't really matter. I think this thing does literally nothing. I'm still not getting how I can miss something, because if I'm missing something, is it, by the way, I wonder, so that's like the number we get in here, and here I guess we will get something that is way bigger again, or will we get a number that is smaller? Yeah, that's still super big number. So but that actually works then both, right? I can overcount when I put more stuff into local counts, and then just like sum them and put that as my number, or I can undercount depending on the input essentially. That thing is not thinking about like, okay, I can at least try to see if I can count it for smaller example, and then just like this bigger example, I can say, okay, I give up. Let's try to make it, okay, this stuff I commented out and I will reuse it now. Okay. Count arrangements too. And what I will do here, instead I will create a hash map. Yeah, I wouldn't mind a hint. At this point, I'm okay with hints. Local counts. We push the, so what is the difference, by the way? No. It shouldn't be a hash map. It should be just, it still should be a vector, but it should be vector of my split list and local parts that don't depend on each other. Yeah, makes sense. This way I will avoid overlapping things, right? Split. What I'm because with my recursive logic, I don't have it like at the same time. I can. You mean if we have distance more than 3 between two numbers? Yeah, those pieces cannot be removed, indeed. Okay. But will it still guarantee that I don't count same stuff twice? Because well, we can try it. Let's quickly try it. If it fails, I will give up for today with part 2. We can do so in principle, because then because then the interesting thing is then if I split it in those parts, will my like dynamic programming logic still make any sense? I'm not sure. But let's see. Yeah, we can do iter, we can actually do split here. I need to go through this thing and oh well, that won't be that easy either. I will better write a function. Otherwise, split non-overlapping. So that's what I want to get. And so I will do iter, I will do enumerate, and I will get index and number, and then of course, and then I will also create this, return it. Combine the solutions and true. Index. Yeah, if index larger than 0 and index init index -1 minus is larger than 3. Oh man. I actually need to also have this like previous list. Previous index will be index, I guess, and index larger than 3. Push it from previous index. To current index, I guess, -1. Yeah. And that stuff I need to it doesn't like it because of into iterator cloned. So that's like split non-overlapping stuff. Let's see. Non-overlapping arrangements, which will be arrangement. Let's see if this thing does anything. And I want for now, I will disable this part and just run it with the first thing, because then I can verify if it does anything useful. Of course, it returns nothing. Non-overlapping arrangements. Why? I wonder. Previous index into iter. So 1 4. Is there actually a no. That doesn't make sense, because 1, 4, 5, 6, 7, 10, 11, 12. They're all overlapping, no? I guess it's only something that I can do after I'm already in recursion. Yeah, because then I think it doesn't make sense here. But here, for example, 7, 10, 11. Stop. Like all possible arrangements are always overlapping? No. Yeah, they are, because otherwise they're illegal. If you have non-overlapping thin pieces that can't be removed. Count on 4, 5, 6, 7 and on 10, 11, 12, 15. You mean piece like 10 cannot be removed? Yeah, 10 cannot be removed. How do you determine that? Because, okay, 7, and if distance is actually equal to 3, not 15. Yeah, 15 also cannot be removed, right? Was mandatory. Oh God, I know already. Because, okay, even if you try to split them, I think it still wouldn't really help me because I also undercount stuff. So like, even if I split somehow and figure that out, I still won't arrive at correct solution, I feel. Because, yeah, I had another bug in the code. I think, yeah, I don't really get the idea about splitting, I must admit. I will just probably for now pause with that because otherwise I won't really solve it anyways. So for now, this stuff, I will just comment it out. Let me look at that. If I see any other way to quickly try, I will probably finish for today. Will be Thursday. I actually didn't do it, but well, eventually it was bound to happen, I guess. If we're cheating, let's actually cheat like completely. Maybe let's look at somebody else's solution. Nah, that I would rather try to solve it tomorrow with a fresh head. So I still was doing something wrong here. When I was going through this local counts, I think that was one of the problems, right? I was getting derived count, which was 1. When I started head of a tree and then I take this stuff, I for now just go through all branches and I sum them even if they have overlapping solutions. I shouldn't do that. Instead, after I went through them, I need to go through them again and then sum the numbers they contain, I think. So instead of doing this, I should remember. So let's call it branches. And here, does that produce problems? First and last number. Ooh, but can I remove this? I think first and last number don't count. I don't think we can ever remove like, yeah, true. Oh God, that's in this example. Yeah, okay. That is like one thing, right? Where I undercount. Well, that is true. That actually makes sense. But how can I fix it then? So if I look at, I can just add 0 and 22. Yeah. So I can just take this and add. So then I can just make it mutable, I guess. Yeah. Where I then can essentially push stuff in the end, which will be arrangement. Oh God, that looks quite ugly, but plus minus 1. It's always plus 3. And then can I do it in reconstruct arrangement? I only use it in the second part. Yes, I only use it in the second part. Show differences. Oh, actually, I just can avoid doing that, I guess. And then I can do arrangement without start. And then let arrangement will be so not the append, of course. Not the most beautiful way to do that, but why not? So that's kind of the thing here. Now, if I try to run it, well, now it's identical to the previous version, so it doesn't matter. Oh, something broke, yeah. That's like the huge thing, but if I now try to do the count of keys, that should in principle be correct, right? And an arrangement sort. Yeah. Let me first see if that improves something, and then I'll try it. Okay, thank you. That worked. Of course, the problem right now is that thing doesn't really help with that. So I wonder if I still try to run it on a very big example. I think it will fail because it will be too huge, the hash map. But we can try. At least we got both sample inputs working. Yeah, that will be like forever now. I also wonder what happens with my memory. 2427. Well, I have a lot of memory, so I think it will run for some time. But I guess I don't want to push it too much. That's too slow. Anyways. Really? You were running it for 5 hours? Whoa. And it terminated in the end. That is crazy. But now the thing is, we did something still wrong here. So, okay, I feel a bit recharged. I will try to. Okay. So I will not do this non-overlapping stuff. I will try to do. So this stuff still will be super huge, of course. But I will move that thing later here. Doesn't really matter where. I'm using count arrangements too, right? So I can modify it easily. Now I can try to do, okay, so we never remove beginning and end, which makes sense. We then do this stuff, and here, local counts. We need to push derived count somehow. Oh, that's by the way count arrangements too as well. Should be at least. Oh, I wonder if it will change anything for us since I changed that. Yep, it did. Yeah, because of the second thing, right? So local counts push derived count. Yeah, I feel that this part of logic is what is wrong here, because that's where I probably end up counting things multiple times. But putting all arrangements in a list or a map. True. True, because then it will end up being too big anyways, right? So like my the whole like count thing won't necessarily work. As long as I add more stuff there, it will only grow. Here though, I wonder if I can just simplify to be like one level long only. Arrangement. Yeah, when I think about it, I think my arrangement is always sorted so that already is there. And here it will always be sorted as well, because when I remove elements, I don't switch them. I have the split function, which I can try, but so like that's different thing, right? If you look at this number, for example, that we never can remove, then $19 is 4 away, 11 is 4 away too, so those numbers are not removable either. So in essence, I can split on stuff that is... Okay, I will try that again. I think I understood the idea about not splitting it there now. So if index larger than... what do I want to get here? Where is my magical thing? Here. So here I can, actually I will put those as well for simplicity. And here, which numbers are more than 3 apart from neighbors, right? That's the condition. Or like 3, actually exactly 3 apart from neighbors. That's the thing. So this number, so this is like first cluster, I guess. 1, 4. So this is like a second cluster, or beginning or end. Five and 6. 10, 11. 7, 10, 11, 12, 12, 15. So it's kinda... 15 was never removed, 16 was never removed, 19 was never removed. Then... or a cup left and a cup right. 5, 6, 7. So then we can 12, 15. This is one like border, right? So this is another border. 6, 7. Actually, I need to select my order, I guess, from the beginning. Then this is like too far. Yeah, not removals. Yeah, makes sense. Because then 12 is not removable, then I guess. Yeah. Then we get like 15. 15 actually also not removable. 0, 1. So this distance is 3. It says distance 1, 1, 1. That makes more sense. 1, 1. Because I need to select my direction. Otherwise, I will confuse myself. 19. And of course, those two. And then I can count this one, I guess. 7 is not removable. Why? 7. Because then I guess both directions are correct, right? 15. 12. Yeah, true. True, because 12 and 7. How do I arrive at that? So I go from here to 15 and 12. So both numbers that... okay, I get it. Both numbers that are distance to each other are not removable, right? Because if you remove one, then you get always distance that is more than 3. Gosh, wow. Okay, that makes sense. I guess we can then do this. So if index larger than 0 and index minus 1 is equal to 3, then go into the recursion 4, 5, 6, 7. Then 11, 12. Not 3, because we also have 15. 16 is also 3. Okay, 16 is also not removable, I guess. Is it? Yeah, it's not. It's not. Okay. Yeah, makes sense. So, but in any case, I first need to mark them, right? I need to first actually extract this stuff, because then actually it's easier to do it differently. We can do one case is missing in general. Okay. So those will be indices of non-removable elements. And here, so I can already put 0 and last element there. Then, okay, it will be super slow, but I will say if or actually I'm putting indices, right? So if init index minus 1 previous number equals 3, then we push index. Yeah, it should return v. Sure. And then if number init index plus 1, that is still all right, because we already put this there and it will never be executed, I guess. Minus number is equal to 3, we push index, right? So that, I think, is what our non-removable things are. Let's put none here, and then we just do arrangement non-removable. We can do debug. Well, should I put both usize and u64 there for simplicity? I guess so. Index num, because otherwise it's super hard to read. And here then it will be init 0. need to dereference. Okay. That looks so ugly. But okay. Okay. Let's see. Did we get correct list here? So we get 0, 12, 1, 4, 7, 10, 12, 15, 16, 19, and we get 19 two times here, but doesn't matter. Yeah, of course it panicked after that. But okay, we got non-removable elements. Now I guess then we need to send lists that are, shall we do it? Yeah, I guess let's just do it into this thing. Hash set. I actually don't need, I think, indices here. So I think at least. I then can do if for num in iter vector contains, oops, this is set. Yeah, okay. And so the one thing though, I still need to remove this stuff, right? So I guess, yeah, because if I have indices, I can see the difference between indices too. Oh God, this is so crazy. I really feel that we kind of overcomplicated very much because this is a tad too crazy for this stage in the game, I feel. But okay, so we got this, and we can then take the non-removable. Actually, we can just call it from here. So let's rearrange this stuff. For index in init. So those will be vectors, right? Non-removable will be, yeah, I guess I will start next stream with looking through simple solution. I know a couple of other people who solve this and who usually end up with way simpler stuff than I do. So I think Sophie Alpert is one. She usually has really good solutions, and she writes in Python, so it also is way shorter and easier to read sometimes. But yeah, non-removable we got. We now need to do, what do we need to do? We need to see if the stuff that we want to end up with 4, 5, 6 is like, essentially we need to take the numbers that are not continuous here, right? Right. So if index, we actually need to write, we need let mute previous split index. So index minus previous index is larger than 1, then we'll say previous index. True, I should. But let's first finish with this stuff. So previous index, we just do this. So we know that this is correct. And then, actually, I can also change my logic, right? I can take... yeah, no, it will break then if I try to change it, because otherwise it relies on it being contained there to not go out of the bounds. But here, if we take this index minus previous index, and it's larger than 1, then we need to do init and previous split index. This is end of interval, right? So we take index init previous split index to current index. I think I'm doing something wrong, but okay. Which you then can into iter and collect split and right, something like that. And then we can say previous split index is equal to index, I guess. Well, naming at this stage in the game already goes out of the window, I feel. That's why. Chunk, I guess. This is chunk indeed. This stuff we don't need. This is V, and you are correct, we need to also sort this stuff, right? Thankfully, we can just do it like that. Non-removables sort, and then non-removables. Okay, let's see if it gets us anywhere. Oh, I always super confused about this. Oh, something broke. Well, what doesn't it like? Oh yeah, of course it wants. It doesn't want references. I know that there is this syntax for inclusive range, right? I always forget about it. I guess I'm too used to using non-inclusive ranges. But yeah, you are correct. It should be probably this. And we also need to do cloned here, right? Yeah. Okay, let's try again. We got a tad too much things. We got 7, and we got okay, 1, 4, 5, 6, 7. So we need to get this stuff, right? And we need to get this stuff. So 7 should be there. But the others, we can go like completely. This is not a very beautiful logic, but we can go completely crazy and just remove stuff from this chunk. So you can do filter. Oh no, that will be also bad, I guess. I will probably do something number there. So, oops. Expected found. Oh yeah, sure, that won't work. I got those indices, and then I need to also adjust my previous split thing. But then in non-removables, I probably should also adjust it here, all this, shouldn't I? Is there a difference then? I don't, no. All this will be, like the moment I discover it. Yes, okay, this is, I didn't need two indices. I think at least. Let's try to comment it out. See this. Will it still work? Yep, it does. Okay, so I really didn't need two indices. And yeah. Split not non-overlapping. Okay, shall we now try this? So let's call it subproblems. And then we can do for subproblem in subproblems. Total is 0. Subproblem. Those I will need to iterate. Yeah, I will into iter them. And then we can do counts arrangement. And then total, I can say count this, which is crazy because then my counts can be way simpler. But sum total, let's see if we have arrived at this solution. No, what else? 6. Why? Maybe is there a difference between recursion product? True, we shouldn't sum them, we should multiply them. Shit, true, because in each branch we will get well, since I'm doing this, I can do this as well. Some, and of course 0, 1. Yes, true, they're independent, so all combinations of them will work, right? Whoa, we solved it, it seems. Shall we try it on the main input? I want to try it in a REPL, because that will be more epic if we actually solve it. This is so far the longest stream. So that works for part 2. We got really big number. Let's see if that's really big number. Woo! Thank you, Thomas. We solved it really collectively. I think this was my first pair programming session via live stream, which is pretty cool. Yeah, second sample worked, and now the whole solution also worked. So we can also just say, yeah, I will just copy this magical number. Yeah, we did it. And actually, in the end, it works very quickly. It's 120 microseconds, which is nice. So day 10, right? Do we use, I will just remove then the old count arrangements. I will then remove the 2 here, so it will be just 1. Oh wow, so you had even more edge cases than that? Gosh. By the way, I don't need this in because now it knows what it needs, right? This stuff is, by the way, absolutely useless because like counts that it does. Like I will just add to do because I won't do it today. Refactor to be a simple hash set to count arrangements since counts are not correct. So actually it can be even faster. Ah, okay. Oh, well, okay. That's crazy. Yeah, I guess mine doesn't contain something like that. That's actually a big problem when you think about it. How do you design inputs for those puzzles that are not, that are not super unfair? Sometimes it happens that some people get something that is, where am I? What am I doing? Get at CRC. Yeah. Yeah, true. But then you see, it depends. If you kind of already know that it's there, it's easy. If you don't, it can take you multiple hours to figure it out. And there was some people who were really angry last year because they got some tasks that contained some very like weird edge cases that other people didn't. And then if you try to compete for leaderboard, it's quite annoying. But yeah, I get it. So days 9 and day 10. Yeah, that's one thing. The problem with paper is that I can't really stream it. I have iPad. I wanted to actually try to connect it and try to draw as well because I think it will also be a bit nicer when I try to think about the problem. But yeah, it's tough. I'm a bit afraid that then stuff will become a bit less. But this is arrangements. But okay. A bit less stable when I stream. So thank you so much. Today we had really intense day. But in the end, thanks to Thomas, we solved day 10 part 2 as well, which was so far the craziest task relay. It's like non-standard dynamic programming kind of thing. Yeah, I guess I learned quite a bit today. Hopefully you too. See you next time. I will be streaming again on Sunday. I will be doing day 11 review. I always solve one day in a week without streaming for just enjoying it. And days 12 and 13, hopefully. We will see if I can actually pull it off because complexity is escalating quickly now. Yep. Thank you. See you all next time.